Hello everyone. Today we are going to dive deep into one of the most important documents ever written in the history of science, Alan Turing's 1936 paper on computable numbers. Seriously, this one paper is incredible. It didn't just define what a computer is before anyone had actually built one. It also revealed some shocking, fundamental limits to what we can ever hope to know.
But here's the thing. Before Turing could even think about inventing the computer, he was trying to solve this question. Back in the early 20th century, this was kind of the holy grail for mathematicians. They were dreaming of a single, perfect method, some kind of ultimate machine that could prove or disprove any mathematical statement you could possibly throw at it.
And you really got to understand the context here. We're in a time with no digital computers, no laptops, nothing. This was all happening in the world of pure thought experiments. Mathematicians were wrestling with the very nature of logic itself, trying to figure out if math was this perfect, complete system where every single question had a definite, knowable answer. And this massive challenge actually had a name, the Entscheidungsproblem. Yeah, I know. Let's just call it the decision problem. The goal was to find a universal algorithm, a sort of magical recipe that would act like a universal truth machine. You'd feed it a statement, and it would spit out true or false. Simple, incredibly powerful, and, as it turns out, a truly revolutionary idea.
Now, to even begin to tackle this massive problem, a 24-year-old Alan Turing realized he had to go all the way back to basics. The decision problem asks for an algorithm or a method, but what does that actually mean? Nobody had a really precise, solid definition. It was just one of those things you kind of knew when you saw it. Turing knew that just wouldn't cut it.
So his approach was absolutely brilliant. He thought, okay, before I can define this big, complex idea of an algorithm, I first have to perfectly define its smallest possible part, a single computation. And the way he did it wasn't with a bunch of crazy formulas, but by thinking about something super simple, a person doing math with a pencil and paper.
And this, right here, is the stroke of genius. He imagined a machine that acts just like a human who's computing something. It's got paper, which he called a tape. It can read what's written on the paper, it can write something new, and it has a state of mind, which is just a very limited memory of what it's currently doing. And that's it. This incredibly simple analogy was the key to everything.
So he takes that analogy and he builds a formal mathematical model from it. He called it the automatic machine. We, of course, in his honor, now call it the Turing machine. And this wasn't a physical thing with gears and wires. It was an idea, the abstract blueprint for every single algorithm that would ever exist. So what is this machine really? Well, it's beautifully simple. You've got an infinite tape, like a huge roll of paper towels, divided into squares. There's a head that can read and write symbols on one square at a time. And the most important part, it has a table of rules, its M configurations, that tell it exactly what to do based on its current state of mind and the symbol it's looking at. Every single thing this machine can do boils down to these four incredibly basic steps. Read, write, move, and change state. That is all. And here's the mind-blowing part. Turing argued that any mathematical process, no matter how complicated, could be broken down into a sequence of these tiny elementary moves. And check this out. This table is straight out of his 1936 paper. This is what a program looks like for a Turing machine. It's just a set of rules. It says if you're in state B, print a 0, move right, and switch to state C. From C, just move right and go to E. From E, print a 1, move right to F, and from F, move right and go all the way back to the beginning, to state B. This simple little loop just cranks out the infinite sequence 0101 forever.
Okay, so making these little specialized machines is cool and all, but this next part, this is where Turing makes a truly profound leap that honestly changes the world. He started to wonder if he could take this whole idea one giant step further.
You see, each of these machines was basically a one-trick pony. They were hardwired to do one thing and one thing only. That 0-1 machine could only ever print zeros and ones. But what if you could build a single machine that could do the job of any other machine you could dream up? And there it is, the lightning strike moment. Turing proved that yes, it is possible. You could design one single special machine that could read a description of any other machine and then perfectly simulate it. This was the universal computing machine. And the crucial difference is this. For a specific machine, the program is the machine. The rules are baked into the hardware like a pocket calculator, but for the universal machine, the program is just more data written on its tape. This is the birth of software.
The universal machine first reads the instructions, the program, off the tape, and then it executes them. It's the difference between a calculator and the smartphone in your pocket.
So now, armed with this unbelievably powerful idea of a universal machine, Turing could finally go back and answer the original question, that big decision problem. He finally had his rock-solid, airtight definition of what an algorithm is.
He'd just conceived of a machine that could compute anything that is computable. But are there problems that are uncomputable? Was there any problem that this ultimate machine would be completely unable to solve?
To find out, he came up with a brilliant test case, which we now famously call the halting problem. Using his own terminology, he asked, could you write a program that can look at any other program and tell you ahead of time if that program is circle-free, meaning it will eventually finish its job and halt, or if it's circular, meaning it will get stuck in a loop and run forever?
And his answer was a bombshell, a definitive, logic-shattering no. He proved with absolute mathematical certainty that no such program could ever be written. Now, it's not that we just haven't figured it out yet. It's that a solution is fundamentally, logically impossible. Some problems are just beyond the reach of any computation.
And this is the final checkmate. It all connects back. The decision problem asks if we can decide if any logical statement is true. Well, the question, will this program ever halt, is a logical statement. So if you had a magic machine that could solve the decision problem, you could just ask it about the halting of any program, which means you would have solved the halting problem. But Turing just proved the halting problem is unsolvable. Therefore, boom, the original grand challenge, the decision problem, must be unsolvable too. There is no universal truth machine. Game over.
So just think about that. In one single paper, a young Alan Turing gave us these three world-changing gifts. He gave us the very first formal definition of an algorithm. He gave us the theoretical blueprint for every single software-driven computer we use today. And, just for good measure, he showed us that there are concrete, absolute limits to what computation and logic can ever achieve. It's just staggering.
You see, this paper is about so much more than machines. By defining the boundary of what is computable, Turing also drew a line around what is mathematically knowable. And it leaves us with this huge, fascinating, and kind of unsettling question. If there are problems that are impossible for even a perfect theoretical computer to solve, what other truths might be out there that are just forever beyond our reach?